about this. On Wednesday, I made the mistake of not getting back to question 1810 and finishing such. I don't know why I did that, but I did that. So let's get back to 1810 now and get that taken care of before we dig further into analyzing Bronsted-Lowry acid-base systems from a quantitative standpoint. Because before you can do that, you have to be able to write correct equations for any reactions that occur in a Bronsted-Lowry acid-base system. So we start with the reminder. In order to write correct equations for reactions that occur in any system, this is impossible if you don't know what's in the system. But if you know what's in the system, then you're off to the correct start. Then you got a chance to play the game and win. And how do we pay attention to what's in the system? By writing an inventory, a principal species inventory. Principal species because for any reaction of consequence that occurs in a system, it's got to involve the principal components of the system. And how do you make this principal system inventory? You have to know the chemistry which occurs when the system is prepared. We've already established the ground rules for that. Briefly, pure substances, that's it. That's the inventory. Water solutions of strong acid, hydronium ion conjugate base. Strong base, hydroxide ion conjugate acid. Weak acid, the weak acid itself. Weak base, the weak base itself. And for all cases, when an ionic compound is the source of the acid or the base, then in order to write the inventory completely for principal species, you will also list counterions. Which means, when you look at a chemical formula, which you should have learned in 2045, you got to know if you're looking at the formula for molecular stuff or ionic stuff. And in general, molecular stuff, a formula which is composed strictly of non-metal components, with the exception of ammonium ion materials. So we proceed. After the inventory, you select from the inventory the strongest acid, the strongest base. Because if any H plus exchange is going to occur in a system, it's got to involve the strongest acid giving H plus to the strongest base. And then the last part of the task is the reaction for which you've written the equation, a large extent transformation or a small extent transformation. Rule of the road, look at the reaction equation you've written. Identify the reacting acid and the product acid. Same applies to bases. If the product acid is weaker than the reacting acid, you've gone significantly, so to speak, from more reactive to less reactive. Such a process is expected to proceed to a large extent. But if you go from a weaker acid to a stronger acid, then you will expect the reaction to proceed to a small extent. Less reactive to more reactive. Which accounts for why we inventory water solutions of weak acids and weak bases as we do. Now last time we looked at parts A, B, C. Let's now look at part D. Add water to aluminum nitrate solution. Right now on your paper, I want you to write the principal species inventory for the aluminum nitrate solution. In this inventory, have you written the formula for water? Have you written the formula for nitrate ion? Have you written the formula for hydrated aluminum ion, which is a hexahydrate? If you have those formulas, you've got the correct inventory. If you don't, you didn't write the correct inventory. To this system, we're adding water. What's the strongest acid in the system? Use the acid-base table as a crutch as necessary. It's the hydrated aluminum ion. Strongest base? Water. So all you're really doing when you add water to the aluminum nitrate solution, given that in a water solution of a weak acid like this, or a weak base, in that solution there always exists equilibrium between the reacting solute acid or the reacting solute base for the weak stuffs with water plus hydronium ion conjugate base for the acid solution, hydroxide ion conjugate acid for the base solution. There we have it. Reacting acid, product acid. Which one is stronger? This one is much stronger. So the extent is small. This, of course, is the conjugate base of this, the reacting acid. Now E. E is rather an interesting system in that we're taking something away from this system. Let's get at E by looking at the reaction equation we have on the board. We recognized that this equilibrium is alive and well in this solution. What operation did we engage in for this solution? We added water to it. The instant at which we added the water, this equilibrium is killed. Therefore, since we didn't add something different to the system, the reaction which has got to take place to get us back to equilibrium is either this in the forward direction or this in the reverse direction. We added water. And the reaction equation itself tells you something. What's this reaction equation say to you? It says, by this process, in order for hydrated aluminum ion to function as a source of hydronium ion, and in so doing get converted to its conjugate base, aluminum ions, hydrated aluminum ions, have to engage in collisions with what? Water molecules. That's what this thing says. I don't know if you learn how to read equations for reactions in 2045. But you got to learn them now. You got to let this stuff talk to you. You got to let this stuff tell you what it means. Then you got it, because then you got the understanding part. So does it not seem reasonable? If in order for this reaction to go left to right as written, aluminum ions, hydrated aluminum ions have to meet with water molecules, that if you up the ratio of water molecules to aluminum ions, that's what we did, didn't we? We added more water. If you up the ratio of water molecules to hydrated aluminum ions, do you now not stand a better chance to convert hydrated aluminum ions to products? Sure. So that in and of itself tells us, by adding water to this system, that's what's got to happen to get us back to equilibrium. Now for this very same system, let's imagine we remove water. We evaporate. Well, another way to look at an equilibrium system is like a teeter-totter. You ever play teeter-totter when you were a kid? Or seesaw, whatever you want to call it? Seesaw. When I was on this side, and the seesaw did this, I jumped off. Bam! Ha ha! I said, I got you. Then my seesaw partner did the same thing to me, and all of a sudden it wasn't so funny anymore. With activities like this, you get to be on, what's this thing, America's Funniest Videos or some damn thing? For an equilibrium system, the seesaw is in balance. Right? Here's hydrated aluminum ions and water molecules on this side. And on this side we got hydronium ions and the conjugate base of hydrated aluminum ion. So if I add water, first consideration applied to this system, I now have placed the seesaw in this position. And the only way I can get back to equilibrium is some of the stuff on this side of the fence reacts to become some of the stuff on that side of the fence. Doesn't that account for the reaction that occurred? Now let's play the game in the opposite direction. Evaporate. Now I'm taking away water. How does the seesaw behave now? Zip! Because now this side is heavier because I took some of the stuff away from over here. Okay? So the reaction that's got to occur to get me back to equilibrium is for these things to react and go this way. Then we get back to equilibrium. Same idea here. When you evaporate acetic acid solution, the right to left reaction occurs. For any equilibrium reaction involving water, if you add water, it goes left to right. If you take away water by evaporation, it goes right to left. Nothing fancy about this. Which means you're going to wind up with an acetic acid solution after you perform this process. You're going to wind up with an acetic acid solution whose molarity label will compare how to 0.5. Will it become greater than 0.5? Yes. You're damn right. You made more concentrated acetic acid solution. F. Look at these two formulas. Are they formulas for ionic compounds? KOH and NaHCO3. Are those formulas for ionic compounds? Yes. Yes. And ionic compounds do what when they're dissolved in water? Dissociate. So here's our principal system inventories for each system. K plus AQ, hydroxide ion AQ in water. Sodium ion AQ, hydrogen carbonate ion AQ in water. Those are the PSIs. So I'm looking at this list in order to pick out my strongest acid. What is the strongest acid in this list? In this inventory? K plus hydroxide ion, water, Na+, hydrogen carbonate ion, water. What's the strongest acid in this list? Use the table. Hydrogen carbonate ion. Hydrogen carbonate ion is an interesting critter, isn't it? We already talked about it. It's both a stronger acid than water and a stronger base than water. Interesting species. There are a couple of other species which also have this characteristic that are contained in this table. Their formulas are in our acid-base table. And in order to do the best job I can as I write a formula to keep with correct structure, I write the formula like this. When I write the formula for the ion all by itself. Remind ourselves that the hydrogen atom component of hydrogen carbonate ion is covalently connected to oxygen, not to carbon. Acid, base, products, water and carbonate. What's the extent? Large or small? This acid stronger than this acid, this base stronger than this base. All right. Oh my, I have to take away our teeter-totter. G. For G, I've changed the source of hydrogen carbonate ion to potassium hydrogen carbonate solution as opposed to sodium hydrogen carbonate solution. Who gives a damn? Neither K plus nor Na plus in water solution have any impact on pH whatsoever. But what we're looking at after we write and examine the inventories for G is the recognition that for system G, hydrogen carbonate ion engages in role reversal of sorts, does it not? Role reversal. What's that mean? For this reaction system, hydrogen carbonate ion was the strongest acid. For system G, what's the strongest acid? What is it? Hydrogen sulfate ion. A much stronger weak acid than hydrogen carbonate ion. And for system G, what's the strongest base in this system inventory? What is it? I already told you just a moment ago. It's hydrogen carbonate ion. And when I protonate hydrogen carbonate ion, I make this stuff. And since hydrogen sulfate ion was my H plus giver, I also make sulfate ion. What's the extent of this reaction? Large. So this reaction corresponds to effective conversion of hydrogen carbonate ion to quote-unquote H2CO3. What do we know about this stuff? What's the acid-base table tell us? You'll get more familiar with the chemistry of quote-unquote H2CO3 and hydrogen carbonate ion when you start having fun with this. How many of you have looked at this? It's all right. You got a lot of time for that. What do we know about this H2CO3? Why is this formula written in quotes?
Because it's not actually carbonic acid, it's just hydrated.
It's hydrated CO2. What do we know about the stability of hydrated CO2? Let me ask another question. Do you have any practical familiarity with the stability of hydrated CO2? Have you ever made the mistake of shaking a can of warm beer and opening it? Or a warm soda pop? Shake it up and then open it? You ever do that? What happens? Out comes the CO2. Because this hydrated CO2 stuff isn't very stable. Why isn't it very stable? Put another way, do you expect CO2 molecules to stick rather strongly to water molecules? Yes or no? No, why not? Why not? CO2, linear, not polar. How about water? A highly electric molecule. Quite polar and hydrogen bonding. So fairly weak intermolecular attraction forces between water molecule and CO2 molecule, which accounts for why it isn't very stable. See, one of the neat things we're going to do this is you talked about this polarity stuff and this molecule being polar, this molecule being not polar, and stuff like that in 2045. But now we're going to talk about the consequences of these properties. Then it'll become much more real to you. So we know that this readily falls apart into this stuff and this stuff. And this stuff has a strong tendency to leave the system. Not only because it's gas under normal laboratory conditions, but because it isn't polar and has a little, not much tendency to stick to this stuff. Are you familiar with any chemistry that you may have seen before? Of this nature? Any chemistry where CO2 comes rolling out of an aqueous system? How about that, Alka-Seltzer? Let's take a look at Alka-Seltzer chemistry. Beaker from your laboratory, half molar sodium hydrogen carbon. I want this one first, doesn't matter. From the laboratory, sodium hydrogen carbonate solution, half molar. Let's put in a good slug of that stuff. Half molar sodium hydrogen sulfate solution. If the chemistry we have just finished discussing is correct, what do you expect to see when I dump a good slug of sodium hydrogen sulfate solution into this beaker, which now contains hydrogen carbonate ion in substantial quantity? How about frothing? Alka-Seltzer. How many of you have seen Alka-Seltzer? Well, let's see Alka-Seltzer again. Look at that wonderful stuff. And the neat thing about it is you now know why this happens. That's what counts. So on we go. H. What's this mean? What does that mean? Excess. You know, abundance. I do this stuff. Students do this to me. I've asked students when we talk about fundamental aspects of thermodynamics, which we really are doing now, but in a more specific fashion when we get to chapters 20 and 21, which means you're going to be talking about energy. So students on exams write this. Energy. NRG, energy. And if I think their answer is rather vapid, doesn't mean much, I will write usually in my comments to their answer this abbreviation. Your answer is empty. Goes back and forth. If you can do this to me, I can do it back. Excess, empty, energy. Okay? Two equations. Got the inventories? For review, we will write the inventories for each system. There's the sodium sulfate solution. There's the ammonium chloride solution. Each of these formulas corresponds to an ionic compound. But when sodium sulfide dissociates and puts into solution sodium ions and sulfate ions, as we've already recognized, the sulfide ions, as our acid-base table reminds us, is a base stronger than hydroxide ion. So you're not going to wind up with any sulfide ion AQs floating around in there, because these sulfide ions react with water to convert the HS minus and hydroxide ion to what extent? 100%, practically speaking. So there's our correct inventory. On the other hand, in the ammonium chloride solution, where I put in the solution by dissociation on preparing that solution ammonium ion chloride ion, this is a weak acid. The pH of this solution will be about 5. But the extent or degree of conversion of this to hydronium ion and ammonia is quite small at best. So the PSI is ammonium ion itself and chloride ion and water. All right? Best acid. Pick it out. Strongest. Tell me. Ammonium ion. Strongest base? What is it? Hydroxide ion. So proton exchange occurs. And as products, I wind up with the water molecule and ammonia. What's the extent? Large. What about the solubility of ammonia in water? Because ammonia, too, under normal laboratory conditions, is a gas, like CO2. Does ammonia show a water solubility like that of CO2? Hell no. You can make ammonia solution up to 15, 16 molar. Because not only is it polar, it's hydrogen bonding. So water molecules and ammonia molecules are quite compatible. They're happy with each other. They exert upon each other strong intermolecular attractions. All right, but our directive up there tells us 2 equations. Now, in order to get at the 2 equations, you got to remember that I said in making this mix, we have this solution in excess, which is telling you that for however many moles of sodium ions and hydrogen sulfide ions and hydroxide ions I have in my sodium sulfide solution, I have more moles of ammonium ion chloride ion, and who cares about the water? Okay? So you got to go back to the inventory. Because by this chemistry, with the ammonium ion in excess, we've wiped this out from the list, from the inventory. All we're doing really is keeping good books. We still have a system with an abundance of ammonium ion in it. Is there anything else in this system with which we can expect ammonium ion to react from an acid-base standpoint, since we've already recognized ammonium ion is the best acid in this list? What is it? HS minus. So here's my second equation. Oops. Large extent, small extent. I heard it. Small. What would you respond to these questions that I ask? Be bold. Don't be hesitant in responding. Yup! Remember this word yop? From ancient Gaelic? How many of you have seen the wonderful movie, at least in my opinion, Dead Poets Society? Like that show? Robin Williams cast in the character of a wonderful teacher because he wanted his students to learn and to understand. Remember his interaction with a student in his class who was somewhat reserved, didn't want to respond? He commanded this student to yop, which means to speak loudly and boldly. Hey, I want you to do the same thing in here. Don't be shy. Yop! As I'm sure you've already recognized, I do this all the time. Now, for this system, I've written the formula ammonium sulfide with quotes on it. Why? How many of you have seen this formula? In this day and age, chemical manufacturers still sell reagent bottles with this label on it. How many of you have seen this formula? Haven't seen it? Good. I'm glad you haven't seen it. Because it's a lie. You can't make ammonium hydroxide. Ammonium ion hydroxide ion. If you could make this be an ionic compound. But you can't make it. Why not? If you put ammonium ion in contact with hydroxide ion, didn't we write this reaction equation right here? Is this not a large extent transformation? Are these ions compatible? These ions kill each other. You can't make this compound. Because to make this compound, you've got to bring together ammonium ions with hydroxide ions, and they kill each other by proton exchange. Well, how about ammonium sulfide? Is sulfide ion not already recognized by us to be a stronger base than hydroxide ion? Well, if I can't make that, I sure as hell can't make that. The sulfide ion is even stronger H plus extractor than hydroxide ion. You write formulas all you want. That doesn't make them real. That doesn't make them exist. I wonder if textbooks will ever learn this. Textbooks for general chemistry. They commit atrocities with this stuff. I mean, atrocities. That's why. You bring one of them books in here, I'm kicking it out the damn door. It has no business in here. This is a place of learning. All right, I've added one. One I borrowed from a quiz I wrote last term, I think. Imagine mixing sodium oxide, solid, pure stuff, with ammonium hydrogen sulfate, solid, pure stuff. Right here. You expect any chemistry to take place if I make this mixture? Put another way, do you think those compounds are compatible with each other? They're ionic compounds. First one's composed of sodium ions and oxide ions. Second one's composed of ammonium ions and hydrogen sulfate ions. Are these compounds compatible? If I put them in contact with each other, will they be happy and peaceful with each other?
No.
No way! Why not? What's going to happen if I put these compounds together with each other?
They'll dissociate and steal hydrogen.
What will happen if I put these compounds together with each other? If I put these compounds together with each other, which I could do, I can go to the lab, get these compounds, and make a mixture of these compounds in a beaker. Would you be of a mind to put your face over this beaker and take a deep breath? If you did, you sure as hell be damn sorry you did this. Why? Why? The ammonia generating from this mixture would knock you flat. You want a face full of ammonia gas? I hope not. Write the reaction equations for that. And if you have difficulty with it, come and ask us. We proceed. One that many of you talked about on Tuesday. We're now jumping back to where we left off on Wednesday's conversation, or following Wednesday's conversation. Oops, I left out the M. 0.50 molar sodium acetate solution. Sodium ions, acetate ions, water. What kind of pH will this solution have relative to 7.0? Greater than 7.0, smaller than 7.0, or 7.0? pH for this solution? Greater than 7.0. Why? Inventory. Sodium ion, acetate ion, water. Is acetate ion a stronger base than water? Yeah. So I know this solution is basic. Will it be strongly basic or mildly basic? Mildly basic, because acetate ion is a weak base. How do you know it's a weak base? Well, our quantitative handle on acid strength or base strength is this K. Ka for the acid, Kb for the base. How are you going to get Kb for acetate ion? Remember the recipe? Kw equals Ka times Kb, where Ka and Kb are for a Bronsted-Lowry conjugate acid-base pair. So if I want to calculate Kb for acetate ion, which I'm going to need to do to wrestle with this problem, because in our table we haven't provided you with Kb values, but we have provided you with Ka values. To calculate Kb for acetate ion, what do I need?
1 over, or Kw over the Ka of acetic acid.
Yeah, Ka for acetic acid. So I got 1.0 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. That gives me Kb for acetate ion, which is 5.6 times 10 to the minus 10. That a big number? Hell no. Acetate ion, very weak base. So the solution is mildly basic. Now, how about ammonia solution? Also basic? Of course. Because ammonia, like acetate ion, is also a stronger base than water. Will the ammonia solution, since these are each half molar solutions, will the ammonia solution have a higher pH or a smaller pH than this solution? This has a higher pH because ammonia is a stronger base. Kb value for ammonia, 1.8 times 10 to the minus 5. Nature did an interesting thing. Gave acetic acid a Ka value, which is equal to the Kb value for ammonia. If you take it to 3 sig figs, they're not equal anymore. Enough said, you can do the arithmetic. Ammonium bicarb solution. Is this solution acidic, basic, and mildly or strongly? Mild acidic, mildly basic, strongly acidic, strongly basic, or is it neutral? Tell me. In this solution, ammonium hydrogen carbonate solution, what is the principal Bronsted-Lowry equilibrium reaction which is alive and well in this solution? Can you write the equation for such on your paper right now? So right now I want you to write. That's R-I-G-H-T followed by W-R-I-T-E. Do it. I repeat my first day's directive. If you make a practice of doing what I tell you, you will succeed. The reaction equation for the principal Bronsted-Lowry acid-base equilibrium reaction that's alive and well in this solution. On your paper, since I told you right now to write this, did you write ammonium ion plus hydrogen carbonate ion? Because in this mix, ammonium ion is the strongest acid in high concentration, and bicarb is the strongest base in high concentration. In equilibrium with ammonia and quote-unquote H2CO3. Do you expect to see bubbles floating out of this pot? Do you expect this reaction to effectively produce quote-unquote H2CO3? Does that reaction equation correspond to a reaction which is large or small extent? I heard a vote for large. Ammonium ion plus hydrogen carbonate ion. Products, quote-unquote H2CO3 and ammonia. Is that reaction large or small extent? Well, it can't be both. Small. Very small. Now, will the solution be acidic or basic? Or neutral? I heard 2 votes for mildly basic. How many support such? 2 votes for mildly basic. Now we got a bunch of votes for mildly basic. Well, I'm keeping my hand up because that's right. How do I know that's right? Ka ammonium ion, 5.6 times 10 to the minus 10. Ka bicarb, 4.8 times 10 to the minus 11. But don't forget, in our last gathering, I believe we talked about Kb for bicarb, which is 2.4 times 10 to the minus 8. And 2.4 times 10 to the minus 8 is 500 times bigger than 4.8 times 10 to the minus 11. And it's about 300 times bigger than 5.6 times 10 to the minus 10. No, not quite. But certainly bigger than 5.6 times 10 to the minus 10. Which means bicarb behaves more strongly as an H plus grabber, a Bronsted base, than ammonium ion behaves as an H plus giver. Which tells me why this solution is this. Now, a couple comments on this, and we'll pick it up from this point on Monday, because our first quiz will depend on how far we get Monday. We are mixing for question 1822 a solution of sulfide ion with a solution of hydronium ion. I believe the sources are sodium sulfide and HCl. But what you're really bringing together is a solution of sulfide ion, no sulfide ion in it, that was a solute, with a solution of HCl. So you're really bringing together hydrogen sulfide ion, hydroxide ion, and of course water, with hydronium ion. And when you do the quantitative inventory, you find out that in this system, you're putting together equal mole quantities of hydronium ion and hydroxide ion. Equal mole quantities of these. Not correct. Not equal mole quantities of these. But you're putting in twice as many moles of hydronium ion as hydroxide ion. Let me get this right. Let me get this right. Let me get this right. Hang on 1 second, please, so I get this right. Yeah, I think that's right. Yeah, that's right. Equal mole quantities of these. Okay? Question. We have mixed equal mole quantities of hydronium ion with hydroxide ion. Will the resulting solution be neutral? Or will it be acidic or basic? Will the resulting solution be neutral or will it be acidic or basic? Don't lose sight of the inventory. Is there anything else in this system which can affect pH? What is that something? HS minus. Will HS minus cause the pH to go up or down? Up. So the system will be mildly basic. We'll pick it up from this point next time.